Hi friends, welcome back to Acharya Gurukula. Today's topic is how to calculate seismic base shear using equivalent static method as per IS 1893 2025 with a solved example problem. In this video, I am going to explain the various parameters like earthquake zone factor, importance factor, elastic force reduction factor, approximate fundamental natural period, normalized elastic pseudospectral acceleration, seismic weight, and after calculating all these parameters using equivalent static method and how these base shear is getting distributed onto each floor of the building. Let us consider a plan of the building whose length is 11.7 meters and width is 8.9 meters. And the details are specified here. Grade of the concrete is used M20 and slab thickness is 0.12 meters. Wall thickness is 0.23 meter. Floor finish 1 kilonewton per meter square. Size of the column and size of the beams are considered as 0.23 by 0.3 meters. Elevation and beam column positioning are given here. The height of each story is considered as 3 meters and the building is considered as G plus 3. That means total number of floors are 4. The design earthquake horizontal force VBDH at the base of the structure and the design earthquake vertical force VBDV at the base of the structure considered the pseudospectral acceleration spectrum shall be estimated as VBDH is equal to AHD multiply with W, which is equal to Z into I into ANH of TH divided by R into W. Similarly, in vertical direction, VBDV is equal to ABD into W, which is equal to Z into I into ANV of TV divided by R multiplied with the weight of the building. In vertical direction, the R is considered as 1 and the discussion of these parameters using equivalent static method is given in the below link. Now, how to consider the earthquake zone factor? The theory part is discussed in the link that I showed in the previous slide, and we'll discuss here how to consider the earthquake zone factor. The value of the peak ground acceleration divided by acceleration due to gravity to the considered towards the estimation of the effects of design earthquake shaking on the structure corresponding to the return period and the earthquake zone in which the structure is located. Now here in this case, the building is located in Hyderabad, which is in zone 2. Now the zone factor for Z is equal to 0.075 for limit state method and 0.05 for working stress method. And the return periods are 475 years and 175 years respectively. Now a tabular column is shown here which the return periods and the zone factors are given. Now, this table is provided in IS 1893 Part 1 2025 as per the clause 6.2.2.2. So here, wherever the parameters which are discussed in the IS 1893, the clauses are given with red color in the subsequent slides. The importance factor. The importance factor I to be used in the estimation of the design acceleration coefficient of the structure shall be taken as specified in the respective part of IS 1893 depending on the type of the structure. So as per the new code, that is IS 1893-2025, the structures are divided into 4 categories: normal structure, important structures, critical structures, and special structures. So irrespective of the type of the structure, the code IS 1893-2025 is considered, the importance factor is considered as 1. Then the elastic force reduction factor. The elastic force reduction factor for special moment resisting frames, that is SMRF buildings, for normal structures, for building set 1, the R value is considered as 5 for horizontal direction and 1 for vertical direction. Next parameter is how to calculate the approximate fundamental natural period, that is TA. The approximate fundamental translational natural period T of oscillation less than 50 meters in height shall be estimated by the following expression. Now for RC building, the expression is given TA is equal to 0.075 h to the power of 0.75 divided by under root of a big expression is given here. So now, if you see the numerator, the h value we consider as 12 meters. This 12 meters is the total height of the building that we consider in this example problem, divided by here other parameters are given in the denominator of this equation. So 1 plus 0.02 rho cc. This rho cc is the structural column density, and rho mv is the structural masonry density, and this rho csw is the structural wall density parameter. Now here in this case, first we'll consider without infills, and then we consider with infill case. So both cases we considered in this example, and we'll see the variation of the fundamental natural period. Now let us consider the rho cc. How we calculate this rho cc is the rho cc is the structural plant density of all concrete. The approximate fundamental column at the base of the building. It is the ratio of the total area of the column to the total plant area. Now, if you see, this is the plan of the building. And the column size is 0.23 by 0.3 meter, and the total area is 3.8 plus 4.3 plus 3.3 multiply with 2 meters plus 3.3 plus 3.3 meters. So that is 11.4 by 8.6. So this is the total plan area of the building. Now the total area of the column is 0.23 by 0.3 is the cross section of the column member. That means how many number of columns are there in the plan. We'll see in x direction we have 4, in y direction we have 4. So that means 4 into 4 is equal to 16. So 16 into 0.23 by 0.3, which comes 1.104 meter square. Now the ratio of these two gives uh, the rho cc parameter. That is TA is equal to 0.075 into 12 to the power of 0.75 divided by under root of 1 plus 0.2 into 0.011, which comes around 0.4618 seconds. Here in this equation, we did not consider any masonry related parameter. Now, Now we'll discuss the rho MV parameter. Rho MV is the structural plant density of masonry infill wall alone at the base of the building in the considered direction of shaking. It is the ratio of total area of walls along X or Y direction to the plan of the area. Now, the area, sorry, along x direction, the external walls, the total area of the external wall is equal to 3.8 minus 0.23. So here in this case, we consider only the wall area. So that means, you see, this is a yeah, so you see, this is a 3.8 meter. So in this 3.8 meter, we consider the wall area. So the wall area means the total length of the wall in this bay is 3.8 minus half of the column width in this direction and half of the column width in this direction. So that means 0.23 by 2 and 0.23 by 2. So that means 3.8 minus 0.23 by 2 plus 0.23 by 2. So that is what is given in this. 3.8 minus 0.23 by 2 minus 0.23 by 2 means 0.23. Like that, for each length, we consider in the similar way. Similarly, for 4.3 minus 0.23 by 2, 0.23 by 2. Then we'll get 4.3 minus 0.23. Like that, we consider the entire length. So the total length of the wall along x direction is 3.8 minus 0.23 4.3 minus 0.3, 0.23, 3.3 minus 0.23. So this is the total length along in one direction. Multiply with 0.23, that is the width, multiply with the 2. So here, in this case, external walls, we are calculating the external walls. So for external walls, this is the total length, multiply with this one, this is 0.23. And how many number of walls, external walls? 1 and 2 along x direction. So that means 2 multiply with 0.23 is the thickness of the wall, and this length, that comes around 4.92 meter square. Similarly, for internal walls. So internal walls, internal walls, the area, the length of the internal wall is same. But when we consider the thickness of the wall for internal walls is considered as 0.12 multiply with 2. So this 2 is the total number of uh, total number of walls along x direction. So this length we already calculated. Like that, how many number of lengths in this direction? This is one and this is another. So that means total 2. So internal wall, external wall, the area along x direction is 4.92 meter square and 2.52 meter square. Similarly, along bidirection also we have to consider. So when we consider along bidirection, so this is y direction. So this is 3.3 minus 0.3. So in the earlier case, we consider this is 0.23, 0.23. But in the other direction, the dimension is 0.3. So that means this is 0.3 by 2 and this is 0.3 by 2. That is 3.3 minus 0.3 by 2, 0.3 by 2. That means 3.3 minus 0.3. Similarly, for 3.3 and 2, multiply with 0.23. For external walls, the thickness of the wall is 0.23. Like how many number of walls are there? Two number of walls along y direction, external walls along y direction. Similarly, the similar kind of calculation you have to consider in for internal walls also. So for internal walls, the total area is 1.85 meter square. After calculating the rho MV along x direction and y direction, then you have to take the ratio. That is rho MV along x direction. That is 4.92 plus 2.57. 4.92 plus 2.57. That is the total wall area divided by 98.04. That is the total area, which is equal to 0.076. Similarly, along y direction, 3.54 plus 1.85, 3.54 plus 1.85 divided by 98.04, which is equal to 0.055. Now, by considering the URM infills along x direction and y direction, how the fundamental natural period varies. The approximate fundamental translation natural period of the building with RC moment resisting and URM infill walls along x and y direction. So here, this term is same. In addition to that, we have to consider the term, that is 0.02 into rho MV. Now you see the equation here, 0.02 into 0.076 along x direction. So whatever the rho MV along x direction value is there, so that you have to substitute here to arrive TA is equal to 0.483 seconds. Similarly, y direction. In y direction, the TA is equal to 0.482 seconds. But with RC moment resisting frames, so that means if don't consider the URM infills, the fundamental natural period TA is equal to 0.4618 seconds. So like that, we have to calculate the fundamental natural period in with infills and without infills. Then the next parameter is the normalized elastic pseudospectral acceleration. So here, before calculating the ANH parameter, we have to consider the site classes. So the shear wave velocity VSI of each layer at the site for normal structures in all earthquake zones we have to consider. For important structures in earthquake zones 2 and 3, we have to consider the shear wave velocity. And the shear wave velocity values are considered using the equations, approximate correlation equations, which are given in the code, 1893 code. So VSI is approximately equal to 80 into N160I to the power of 0.5 for dry sands, where the fineness content is less than 15%, and 80 into N160 I to the power of 0.4 for saturated sands, where FC is less than 15%, and 80 into N160 I to the power of 0.3 for clays. For sands, VSI is expressed for clays where FC is greater than 15%. These correlations are not applicable when N160I is less than 10. A detailed field investigation should be adopted. Then, here in our example, we consider a hypothetical data, assume that the fineness content is less than 15% for soils, and the layer thickness as given 2 meter, 4 meter, and 4 meter. And the corrected SPT value are for a 2 meter layer thickness 28, 4 meter 32, 4 meter 35. And the soil types are dry sand, saturated sands, and clay soils. So now using the these expressions for calculating the shear wave velocity, we calculated the VSI value 423.32 meter per second, 320 meter per second, and 232.43 meter per second. Now, after obtaining the shear wave velocity at each and every layer, now we have to calculate the Vs value by summation of all the layers. So, using the equation given below. So, Vs is equal to sigma I is equal to 1 to n into number of layers, thickness of each layer divided by summation of I is equal to 1 to number of layers into thickness of each layer divided by shear wave velocity of each layer. So here the thickness of each layer means, you see the tabular column here, 2 meter, 4 meter, and 4 meter. So summation of all thicknesses 2 meter plus 4 meter plus 4 meter divided by thickness divided by the corresponding shear wave velocity. Now you see the thickness, that is a 2 meter. For 2 meters, the shear wave velocity is 232.32 meter. For 4 meter, 320. Again for 4 meter, 232.43 meter. Now you see the ratio thickness divided by the corresponding shear wave velocity. So 2 divided by 432.32 plus 4 divided by 320 plus 4 divided by 323.43 meter. So by simplifying, then we'll arrive Vs is equal to 290.41 meter per second. Now, as per the code, for the shear wave velocity 290.41 meter per second comes under site class D. Now, we already obtained the fundamental natural period. So, in the normalized elastic pseudospectral acceleration, that this curve, for this spectrum is applicable only for equivalent static method. For response spectrum method, we have to use another spectrum. Now, for our case, the fundamental natural period is in between 0.46 to 0.48. So that means the ANH for 5% of damping ratio, it comes around 2.5. Now the equations are given for class D, where the structure is above ground. Similarly, in vertical direction, we have to multiply with the delta VTV. Now, this delta VTV is equal to the equation is given for site class D with the variation of the time period 0 to 0 0.01, 0 0.01 to 0 0.1, and more than 0 0.1. So here in our case, the time period value we consider in vertical direction is 0.4 seconds. So the delta VTV is equal to 0.67 we have to consider. The normalized horizontal spectral acceleration of the structure is obtained from the above figure is equal to 2.5, so which I already discussed in the previous slide. And in vertical direction, that we have to multiply with 0.67, which comes 1.675. Now, coming to the another parameter, that is the seismic weight. So, seismic weight of the building without infills and with infills, the calculation is given here. A detailed calculation is given in the YouTube link, which is provided at the end of this slide. The same values we consider here. So for at third floor, the seismic weight is 450.72 kilonewtons. For the second, first, and ground floor, the seismic weight is 582.56 kilonewtons. Now, the total seismic weight W without infills is equal to 450.72, which is in third floor, plus remaining second, first, and ground floors. The seismic weight is same, that is 582.56 for second floor, again 582.56 for first floor, again 582.56 for ground floor. So that means multiply with 3. Then we'll get 2198.4 kilonewtons. Then seismic weight of the building with infills. For third floor, the value is 1007.32 kilonewtons. For second, first, and ground floor, the value is 1690.16 kilonewtons. Then the total seismic load, that is W, comes 6077.8 kilonewtons. Then, after obtaining all the parameters, then we have to calculate the design earthquake horizontal force VBDH using working stress method and limit state method without URM infills. So substitute all the parameters which I discussed in the previous slides. Then we obtain VBDH is equal to 54.96 kilonewtons for WSM case, and 82.44 kilonewtons for LSM case. Similarly, in vertical direction, the value is 274.8 kilonewtons. Similarly, with URM infills, VBDH is equal to 151.94 kilonewtons per WSM. VBDH is equal to 227.91 kilonewtons for LSM. VBDV is equal to 759.725 kilonewtons in vertical direction. Here there is a typological mistake. It is not horizontal, it is a vertical force. Now, as the normalized horizontal spectral acceleration of the structure A and H is identical for both bare frame and infill frame configurations. In this case, the computed base shear is unchanged. So if A and H is different between the two structural systems, the resulting base shear values will also differ. So here if you consider the first case, that is a working stress method case, so uh, ANH value is 2.5 in both the cases. Why? Because the fundamental natural period is like in between 0.6 to 0.8. So for that case, the ANH value is equal to 2.5. Now, if it differs, because TA value in X direction, TA value is in Y direction, has a large variation between these two, then obviously we'll get ANH value is different for these two cases. So in that case, you have to consider VBDH in along X direction, VBDH along Y direction. Similarly, for limit state method, VBDH along X direction, VBDH along Y direction. But in this problem, we don't have encounter any problem. Why? Because the ANH value is equal to 2.5. Then lower limit of the design horizontal base shear. Now, whatever the base shear that we calculated, so is there any limit for that? Yeah, code suggests equation for lower limit of the design horizontal base shear. That is VBDH is equal to 0 minimum base shear value is equal to 0.625 into ZI by R into W greater than or equal to 0.015 into W. Now here you see in our case, the expression for minimum base shear shall apply to the normal structures designed using LSM in seismic zones higher than zone 2 and using WSM in zones higher than zone 3. Otherwise, adopt the code minimum base shear. Now, here in our case, the minimum base shear is obtained. The condition is not satisfied in this case. So that means, so whatever the base shear that we consider, so the same base shear you have to adopt. Now, here, like I is equal to same in this equation, R is equal to, let us consider for special moment resisting frames, R is equal to 5, and weight in this equation, weight is same in both expressions. Here, this to satisfy this condition, this Z value should be greater than 0.12 G. So, the Z value it should be more than 0.12. Now, if I see the tabular column for various written periods, for normal structures, the Z value is higher than zone 2 using LSM. For WSM, it should be higher than zone 3. So for these cases, the Z value is more than 0.12. Now, other case for otherwise, we have to consider if it is not satisfied, if it is less than that, then we have to consider the minimum base shear. Then, after obtaining the base shear, then we have to distribute onto the floor levels. The design horizontal earthquake base shear force, that is VBDH, obtained shall be distributed along the height of the building and in plan at each floor levels as specified under here under. Distribution of base shear force as floor lateral forces at different floor levels is computed as QDIH is equal to WIHI square divided by sigma j is equal to 1 to NWJHJ square multiplied with VBDH. Now, the QIH is equal to 450.72 into 3 square divided by 450.72 into 3 square plus 582.56 into 6 square plus 582.56 into 9 square plus 582.56 into 12 square multiply with the 54.96. So this 54.96 is the base shear value. So which comes around Q is equal to 1.42 kilonewtons. So similarly, the distribution onto the floors has been calculated in similar manner and obtain the distribution of forces on each and every floor. So here this is the case without URM infills. The distribution of forces is like this. At ground story, it is 1.42 kilonewtons. First floor 7.38, second floor 16.61, and third floor 29.53 kilonewtons. And this is the story shear 23.53, 46.16, 53.52, 54.94, 94 kilonewtons. So that is the base shear which is acting, which is shown here. Now, when it comes to the LSM, the base shear is 82.44 kilonewtons, and this is the distribution, and this is the story shear. Similarly, the base shear is distributed use by considering URM infills. The base shear value is 151.94 kilonewtons for WSM and 227.91 kilonewtons for LSM. Now, after distributing the base shear onto floors, then how the force is getting distributed onto the frame elements. The buildings whose floors can provide a rigid horizontal diaphragm action in their own plane, VDIH shall be distributed to the various vertical structural elements in proportional to their lateral stiffness. Now, in buildings whose floors are not capable of providing rigid horizontal diaphragm action in their own plane, VDIH shall be distributed to the various vertical structural elements in proportional to the mass from tributary floor areas. Alternatively, the flexible floor shall be modeled as a flexible diaphragm. In vertical direction, VDIB shall be distributed to all vertical structural elements, including those that are not part of the lateral load resisting systems in proportional to their axial stiffness. So this is the equation for the distribution of vertical base shear. So VDB shall be distributed to all vertical structural elements according to their axial stiffness. Now, the values. Now the vertical base shear values without URM infills and with URM infills. So this is what is the summary of the distribution of forces with URM infills and without URM infills. In next video, I'm going to explain with the same example problem using response spectrum method. Thank you. Jai Hind.